In modern physics, there is a recognized discrepancy of 122 orders of magnitude between the theoretical prediction for vacuum energy and what we actually observe. It is the largest discrepancy between theory and observation in the history of science. This catastrophic error stems from a specific algebraic misstep in standard cosmology regarding Einstein's field equations. This diagram shows Einstein's core equation. Standard models take the cosmological constant, represented by lambda, from the left-hand side and move it to the right. In doing so, they reinterpret a piece of pure geometry as a local vacuum energy density, or rho lambda. But lambda belongs on the left-hand side. It multiplies the metric itself, acting as a global property of the geometry. Resolving the cosmological constant problem requires correcting this century-old misclassification of space. In 1917, Einstein originally introduced lambda to hold his geometric model of the universe static. When astronomers like Edwin Hubble observed redshift in distant galaxies, the physics community abandoned the static model in favor of an expanding universe. Einstein famously called adding lambda his biggest blunder, yet the real error was discarding the static universe. This framework rests on a different axiom. The universe is a static, finite three-sphere. In this model, dark energy pushing space apart is an illusion. Within this static geometry, redshift represents observers registering the phase evolution of a cosmic standing wave. Since space is static, lambda exists as the passive ground mode eigenvalue of the cosmic boundary. General relativity is a strictly local theory. Its equations describe dynamics on a given domain, but they do not define the overall topology of that domain. To find that shape, we look to the minimal topology capable of bounding the universe, a non-orientable Möbius band embedded within a simply connected closed three-manifold. This isolates a totally geodesic two-sphere inside the three-sphere, matching its boundaries to form a Möbius quotient. This defines a strict spatial scale. The band's longitudinal period is exactly pi times r, where r is the three-sphere's curvature radius. Enforcing this specific topological shape creates a rigid geometric cavity that strictly limits the wave modes permitted within it. To find the permissible modes of this cavity, we solve the eigenvalue problem using the Laplace-Beltrami operator on the curved Möbius surface. The inherent geometric twist of the Möbius identification forces an anti-periodic boundary condition on any wave traversing it. Mathematically, a wave completing one lap returns inverted. Amplitude at y plus L equals negative psi of y. This strict inversion forbids constant modes, where the wave number is 0, restricting the universe to a half-integer spectrum. The universe selects the lowest mode, the ground mode, where m equals 0. Higher modes contain internal nodes that would generate anisotropies, violating the uniform data observed in the cosmic microwave background. According to Sturm-Liouville theory, a node-less eigenfunction in this anti-periodic sector is the mathematically guaranteed ground state of the cosmic boundary. We can now calculate the precise scalar eigenvalue of this ground mode across the curved metric. The totally geodesic condition ensures the embedding carries no extrinsic bending information, matching the simplicity of the ground mode. Applying the Laplace-Beltrami operator to this ground state yields an exact eigenvalue of 2 over r squared. As this derivation highlights, that eigenvalue is perfectly equal to the intrinsic scalar curvature of the two-dimensional surface itself. The Bochner identity locks this eigenvalue as a strict lower bound, making this equality unique and topologically protected. Therefore, the observed energy of the cosmic background is exactly identical to the intrinsic curvature of the topological boundary. While that eigenvalue is defined on a two-dimensional surface, cosmological observations take place in three-dimensional space. The Gauss equation serves as the geometric interface to convert the two-dimensional intrinsic curvature into a three-dimensional ambient spatial curvature. Under a totally geodesic embedding in isotropic space, the tensor mathematics reduces to a ratio of 3:1. General relativity then relates this 3D spatial curvature to the cosmological constant. Spatial curvature equals 2 times the observed lambda. The observed cosmological constant is the two-dimensional topological eigenvalue projected into three-dimensional space through a structural conversion factor of 3/2. Combining these factors, the curved eigenvalue of 2 over r squared and the Gauss conversion of 3 over 2 yields the final formula, lambda equals 3 over r squared. The single variable, r, is physically constrained by the Molian gap in the cosmic microwave stochastic, independent of any measurement of lambda. That independent measurement sets r at approximately 5.3 gigaparsecs. Plugging 5.3 gigaparsecs into our formula yields a theoretical lambda value of 1.12 times 10 to the negative 52 per square meter. This prediction is nearly identical to astronomical observation, showing agreement within 2%. Spatial topology derives the exact value of lambda, bridging the 122 order of magnitude gap without requiring new physics. Eigenvalues on a fixed geometry are mathematical constants, making lambda strictly unchanging for a fixed topology. Data from the upcoming Euclid Space Telescope will falsify this framework if it shows that dark energy density evolves over time at greater than 5 sigma. The universe functions as a resonant cavity, holding a stable standing wave. The cosmological constant is topologically protected geometry, the ground tone of a resonant